This is a Minesweeper AI. Just kidding, this is me playing Minesweeper. I'm trying to win the game by clearing all of the squares without stepping on a mine. I'm playing on a custom Minesweeper implementation which can demonstrate all of the AIs that I built. There's a link to the source code in the comments. This is a project that I did a few years ago and I'm proud to show it to you today. As you can see though, I'm not particularly good at the game myself. I'm slow, I sometimes make mistakes, and I'm not accurate when it comes to guessing. This, on the other hand, is a little preview of the AI running. It has been slowed down a lot obviously, so that you can see a bit of what it's doing. What's special about this AI is that it can even do absurdly large Minesweeper games that ordinary backtracking can't do. More demos at the end of the video. But first, for those interested, I'll show you how the AI works. We start with the basic strategy. You probably play the basic strategy yourself when you're playing as a human. It's quite intuitive. Let's take a look at this one, for example, which indicates there's a mine around it. Clearly, it means that the only unopened square next to it must be a mine. Now let's take a look at this 3. Similarly, there's 3 unopened squares next to it, so they must all be mines too. On the other hand, let's take a look at this 3. Well, it's already got 3 flags around it, so the remaining unopened square next to it must be empty and safe to click. We apply this process over and over again until we sweep the entire minefield and either win or click a mine and lose. This basic strategy is able to see through most beginner games and even some intermediate ones with a bit of luck. According to my AI program, it will typically win 80% of beginner games if a random square was clicked when the basic strategy ran out of moves. If, however, we ran the basic strategy at full speed on expert games, then the win rate is quite abysmal. There's some room for improvement. The next step is to calculate the chances of each square being a mine using backtracking. Let's take a closer look at what we need to do. In this position, the simple strategy has no useful moves. However, there are still squares that we can know for certain are safe. There's actually 13 unique arrangements of mines around this particular group. If we looked at all of them at once, then we can figure out that in all of the arrangements, this square on the top right is a mine, so we can conclude that this square is definitely unsafe. Similarly, we can find out that in all of the arrangements, this square on the top left is not a mine, and so now we have found a safe square. All the other squares are mines in some arrangements and safe in others, so they maybe are mines. The probability of them being a mine or not can be determined by counting how many arrangements out of the total they appear as mines, and it can be different for all the squares. At the end of the day, we just really need to know one square that is safe, and we can click on it and progress the game. Damn it. In order to generate those arrangements, I used a technique called backtracking. In backtracking, we build all the possible arrangements square by square. When building an arrangement, we flip through the possibilities one square at a time. In short, backtracking is just a very methodical way of doing trial and error. Let's take a closer look. For the next square in consideration, we first set it as empty, then recursively go to the next neighbor to generate all the arrangements possible. Once all the arrangements where that square is empty has been explored, we then set the square as having a mine and try it again. After we're done with our cell, we go back to our parent and tell it to try the next possibility. Whenever we come across an impossible situation, we stop or backtrack, and then continue with a different attempt that might actually be valid. That saves a lot of useless computation. By going through this process, we eventually end up generating all the possible arrangements. Let's see backtracking in action on some expert games. If you blinked, you might have missed that it very quickly completed a couple of games at the start, which is great. But most of the time that you are looking at it, it's stuck on some larger border like this one. This is because backtracking has an exponential time complexity. If we waited this one out, it will eventually finish, but it could be made a lot faster. As an afterthought, we could also use the basic strategy every now and then, like right now, to unlock a few squares and break the perimeter apart into smaller portions. But the problem with that is, on even larger grids, it will always find an unusually large unbreakable portion to get stuck on. Here it is on an even more massive grid, struggling to do just one game. Surely we could do a lot better. And in the next part, we will. So, can we actually improve on this algorithm to be better than exponential? No. I did some research, and some people have already worked on this. It has been determined that Minesweeper is NP complete, which means that it can't be solved in polynomial time. Well, today at least. They did this by creating Minesweeper situations on the board that simulated existing problems like 3-set. This would prove that there are Minesweeper positions that can only be solved after solving an NP-complete problem like 3-set, which means that, in theory, it's impossible to solve Minesweeper in better than exponential time. However, in theory is usually not the end of the story. In real games, Minesweeper squares that we must calculate form thin lines and perimeters around large blocks. Of course, we occasionally end up with holes in the middle and stuff like that, but those cases can be handled by the algorithm I'm about to show just fine. Cases like the ones needed to simulate 3-set needs thick perimeters with lots of pockets and surface area, which in real games just don't actually happen. It is on this basis that I realized that a very powerful improvement to the backtracking algorithm would actually be enough to solve pretty much all real games of any size. I want to call the new method that I created the Frontier Dynamic Programming method. The idea is that we kind of do what backtracking does, but instead of enumerating all possible combinations across the entire perimeter, we instead enumerate only local segments and somehow stitch those local segments together to form a global result. The method is being animated right now. Let's take a closer look. At any time, we have a set of frontier squares, which contains squares we need to calculate all combinations of lines for. For backtracking, this would actually be the entire perimeter. But here, while we do add squares to the frontier, we also actively remove squares too, to what's called the tail end, when they are not needed. Squares are removed, or collapsed, only when they are not useful to permutate anymore. More specifically, they are removed from the frontier when they don't connect to any of the unprocessed squares by a numbered square. When that happens, it means that by just looking at the combinations of mines in the smaller frontier set, we already have enough information to figure out all the valid permutations of the mines in the remaining squares too. And so the squares that we correctly collapsed from the frontier set are not needed. When squares are collapsed and added to the tail, we no longer store every combination of mines within them. That's only for the frontier set. Instead, we now just store a count of the combinations where this square was a mine. At the end, we can just use that to figure out the probability of a square being a mine. By keeping our DP table up to date, we're going to be able to deduce this new information that we need to put into the tail. So, how fast is this whole thing? The algorithm has to permutate the frontier, so it is exponential in the size of the frontier. By keeping the frontier as small as possible, we keep the processing time very small. After all the squares are processed, we end up with the entire perimeter being the tail. And the tail has the probabilities that we want, the probability of each square being a mine. This is how the algorithm is able to solve a Minesweeper position even if it has a very, very, very long perimeter. This is a slowed down version, which I've added animations to so that you can see what the AI is actually doing. Notice how it sweeps through the perimeter, bringing all of its calculated goodness through. And as long as there aren't too many green squares at once, this algorithm will run very quickly. Remember that the algorithm is exponential in the number of green squares on the screen. Now, let's see it go through 1,000 expert games in real time. If we pause here and take a look at the bottom left for the win rate, we're going to see that it solves about half of them, which is about as good as you can get. And here it is playing some very large games like they're nothing. And here it is playing an absurdly large game. Now I could go higher, but then we're going to run out of pixels. I hope you enjoyed this video. It's my first ever video. Please like and subscribe because I will be posting more things. So stay tuned.